we're going to ask a question: what is necessary for a series, the sum from n equals 1 to infinity of a sub n, to converge? We already have seen the definition, and I'll state it like this. We say the series converges when this sequence, a1 plus a2, a1 plus a2 plus a3, a1 plus a2 plus a3 plus a4, etc. When that sequence converges, this is called the sequence of partial sums, because this is what we call S1, the first partial sum, S2, S3, S4. And so when we look at this sequence, we're adding up more and more terms from the series. That allows us to think of the series, the sum from n equals 1 to infinity of a sub n, as really, in some meaningful way, a1 plus a2 plus a3 plus a4 plus etc. Think of adding all the terms, an infinite number of terms together. We give meaning to that by just looking at adding a finite number of terms, starting from the beginning, together, and then just increasing that finite number of terms more and more and more, and asking, is there a limit to this sequence of partial sums? So here we define S sub n to be a1 plus a2 up to an, and again we say that this series, the sum n equals 1 to infinity of a sub n, converges and has the limit L. We only assign a number to the series when it converges. And this is the value of the series. We say that this will be true if this sequence, S sub n, has limit L. In other words, the limit as n approaches infinity of S sub n equals L. Now, there's an important theorem that tells us one important thing that's necessary if a series is to converge. And I'll show you that in the following way. If the series converges, and say has value L, then as we've already said, the limit of S sub n is L. We can say the same thing about the limit as n approaches infinity of S sub n minus 1. What does one even mean when we write this? Well, S sub n, this sequence, think of the sequence as S1, S2, S3, etc. This sequence, S sub n minus 1, would be S0. We don't define S0. We could just call it 0 if you want. S0, S1, S2. We just reduce the index by 1 each time. And just by shifting the index, it'll have the exact same limit. That doesn't change what's happening when n is really big. The fact that this limit is L means when n is really big, S sub n is close to L. S sub n minus 1 will also be close to L, so it will have the same limit L. And then by limit laws, the limit of S sub n minus S sub n minus 1 will be the limit of S sub n minus the limit of Sn minus 1, which will be L minus L, which is of course 0. But what is S sub n minus S sub n minus 1? We've already seen this is S sub n. S sub n minus 1 is just a1 plus a2 up to an minus 1, which is the previous term here. I should have written that in. So that S sub n minus S sub n minus 1 is the same as a sub n. They only differ with this by this last term. Here we have an an minus 1. Before that, the difference, S sub n minus S sub n minus 1, everything cancels except this a sub n. So that tells us the limit as n approaches infinity of a sub n must be 0. So let me underline what we said. We've said if the series converges, then the limit of the individual terms must be 0. The contrapositive of that says if the limit of the individual terms is not 0, then the series cannot converge. And you can see for yourself that's equivalent. If this limit is not 0, cannot converge, which means it diverges. So if the individual terms have a non-zero limit, the series diverges. Here's an example. What's the sum of 1 minus 1 over n? N equals 1 to infinity. Well, here the individual terms have limit 1. When n is big, you're adding something close to 1 each time. And because those individual terms have limit 1, the series must diverge. So this diverges. The converse is very different. We ask the question, if the sequence a sub n has limit 0, must the series converge? We know if the series converges, the sequence has to have limit 0, but does the implication hold the other way around? That's called the converse of the original implication. And the answer is no. And it's very important to understand why this answer is no. Oops, I apologize. Let me fix this. We saw an example of the harmonic series. This is 1 plus a half plus a third plus a fourth. And this diverges, even though the sequence 1 over n certainly has limit 0, which we've seen before. In other words, having the individual terms tend to 0 is not strong enough to get the series to converge. This still diverges. We showed this in an earlier video lecture. Be sure you've seen that one. We're going to see other examples of the same sort of thing, where you have sequences that tend to 0, where the sum can still diverge. So here's the question. Is there any better way to say what makes a series converge? And as long as we're talking just about positive term series, where all the individual terms are positive, we certainly, if the series is going to converge, we certainly need the terms to tend to 0, but that's not enough. We need them to tend to 0 fast enough. So the sum of a sub n equals 1 to infinity converges. And here we're talking about positive terms. If the sequence a sub n tends to 0 fast enough. Now, what does fast enough mean? Well, 1 over n tends to 0. That's not fast enough. We're going to see in the next section the sum of 1 over n squared converges. We've already seen the sum of 1 over 2 to the n and other geometric series whose common ratio is less than 1 converges. In both of these cases, the individual terms tend to 0. In this case, 1 over 2 to the n, or that converges to 0 much, much, much faster than 1 over n. 1 over n squared also converges to 0. The sequence converges to 0 much faster than the sequence 1 over n. We're going to learn some tests over the next 2 weeks that will give us a much better insight as to what constitutes fast enough. So we won't say more about that.